So I'm going to start a new topic and called a race condition. Okay. And this is another very interesting vulnerability, another different pattern. Okay. And I do have a question and for the pop quiz, and I would like you to answer. So what is a race condition? Okay. Race condition is a very generic term. Okay. So it's when you write actually multi-thread or multi-process the programming, and you're going to actually encounter this term. Okay. So here's a very simple program. Okay. And it shows you a race condition. So this program basically says I'm going to get a balance. This is related to a banking account. Okay, I'm going to get a balance, and now the user is going to actually withdraw a certain amount. Okay, if this amount is less than balance, that is actually the customer withdraw the money. Okay, and if not, then just show the insufficient funds. Okay, for the single process, this is fine. That's no problem. But what if you have a multi-processing? Okay, and this customer send 2 requests almost at the same time. Okay, and so process 1 is going to run this, then process 2 is going to run this again, and they're both running. Now let's see the process 1 just check the balance, get the balance. Okay, let's see the balance is $100. Okay, now before this finishes, the process 2 comes in, another request comes in, okay, and it's going to actually check the balance again. The balance still wants 100 because the process 1 has not finished yet, has not withdrawn the money yet. Okay, after withdraw, let's see $90. After withdrawing, the balance will be $10. Okay, now if you want to withdraw another $90, and you will not be able to withdraw that because you don't have enough money. But the process 2 come right in between here. Okay, so process 2 is going to say, oh, you got a balance of 100, and both processes is going to actually continue on with withdrawing. So the customer is going to get $180, although the balance is only 100. Okay, so that's definitely the security problems because now the bank lose money. Okay, so this is very, very critical for actually the transaction, for the online banking, for a lot of these transactions. Because transactions need to support multiple actual transactions at the same time. They usually support millions of transactions at every second, okay, for this large server. So they will have to deal with the race condition. They will have to, for example, using lock mechanism, using a lot of this the mechanism to make sure this will not happen. Okay, but that's called a race condition. Okay, it's a very common actually program mistakes, and in the multiprocessing and the multiprocessor programming, and you have to deal with that. Okay. So let's look at one specific type of race condition. Okay, and that affects the security. Okay, so this is a very specific one. So I'm going to ask you to look at this code. Here's a code. So this code is actually trying to write to a file in the temp directory, okay, /temp directory. So in Unix, and the /temp directory is a word writable folder. Anybody can write to that folder. Okay, so this is word writable. A lot of applications, they put their temporary data in the folder. Okay. So that's why the folder allows everybody to write to that. Okay. So this program is trying to write to the file called /tempx. Okay. But the program is this is a setuid program. And running with a root as effective user ID. Okay. So, but the programmer was very careful because this is a very privileged program. The program was afraid that the X already exists. Okay, X already exists, and so the program doesn't want to actually to write to this file if this file belongs to other people. Okay, so it actually check using the access. This is a system call. It checked the real user ID. Okay, remember when we talk about the effect user ID. So if you want to open a file, you want to write a file, read from file, and the system always checks the effective user ID to make sure the effective user ID can open that file. But this is the case, it's check the real user ID. Okay, the access is different from the other, the system call. It does check the real user ID. So this one is check whether the real user ID can write to this file. Okay, in my case, I'm running in the seed account. Basically, access check whether the seed can write to this file. And if it doesn't, if it cannot, that means this file belongs to another user, okay, or belongs to the root user. We shouldn't let it write. Okay, the program has the power to write to any file because the program runs with root privilege. Okay, but the program just wants to make sure I don't overwrite other people's the file because this is a shared folder. Everybody can put their the temporary file in here. So it does the right things to check whether the file belongs to somebody else. Okay, if it does belong to, and you don't have a permission, you just go to this branch. Otherwise, it will open the file. Okay, it will open that file and then write to that file. That's what it does. Okay, so it's supposed to be a temporary file. Okay, this program creates a temporary file and wants to write some temporary data into it. Now, there's a vulnerability inside. Okay, not obvious. Okay, now the question is, can you use this program to write to a protected file? For example, write to /etc shadow file or password file. So can you use this program and to write to this file? This program only write to the /temp_x file. Okay, that's the goal. You cannot change this program. Okay, you are not allowed to change the program. The program hard-coded the file name /temp/x, but you want this program to write to this file. Can you do that?
Does the access program check the links?
It check everything. Yeah,
It
check.
will check the permission of that file which is linked.
Yes, yes.
So we can try to link to an existing file which we have access. We can run a program side by side, which will create a file by name X, which is linked to a regular file which we have access.
Okay, so let's look at this approach. Okay, so let's see. This program want to write a /temp_x file. Okay, and that is I can go there before I run this program, right? I can go to the /temp folder. I can create a symbolic link. I can make this a point to /etc password file, right? I can let it point to here, right? So before this, so at this place, I can do this. So before I run this code. Now, can I get this program to write to this file? Can I? Now I do this before this. I change this /temp_x, let it point to another file. The access is going to check. Although access is going to check this file, but it's actually, since it's a symbolic link, the access is going to check the real user ID has the permission to modify that file. It's going to fail, right? Because access check the real user ID. Real UID is a seed. Seed cannot modify this file. Okay, remember we are doing the write w_OK. That means you're checking whether the real user ID has a write permission to this file. Okay, and that, so WOK cannot, okay, so you cannot write to this file. This file is only writable by the root. So now if you do that here, you're going to fail. Okay? Now what you really want is you want to, when we get to here, if we get to here, let's say I'm going to put a 2 here. Let me remove all of this. So we have a 1 here. Now, if I can do this at this point, at 2, okay, at 1, this /temp is still a /temp, a regular file, okay, and then the access is going to check whether the seed can actually access its own file, right, which is okay. But once I get here, if I can magically change this, okay, so at this point, /temp is just a regular file, owned by root, but not by root, by seed. But somehow, after this one is finished, now if I can change this, okay, I can do here, I can change /temp x, let it point to the /etc password file. Now if we look at open for write, will this be successful or not? What does open system call check? Real user ID or effective user ID? Effective user ID, okay? Other than the access, remember, other than this system call, all the other system call, if they need to check the user ID, they check the effective user ID. Okay? So open is going to check the effective user ID. In this case, what is the effective user ID? It's root. It's 0. Right? 0, of course, can modify this file. That file belongs to the root. Okay? So the check here is going to be successful. Okay? And then, of course, then it's going to write to that file. Okay? Assuming the programs take the input from the user. Okay? So whatever is going to be returned to the file is actually provided by the user. Now, if you can do that, and you can actually write something into the /etc password file, okay, and you can create a new account, right? Remember, /etc password file is where the account information are held, right? You can add engine, and you can create an account with UID 0. Essentially, you create a root account in the system. Okay? Now the question is, how can we do that, right? Now if I can make this machine run very slowly, right? These days we have 3 gigahertz of machine. If I have a 1 gigahertz of machine, right, every second to run 1 instruction, if we can do, assuming the computer is that slow, now tell me how you can do that. Assuming you can do a very fast one, okay? And the program, the CPU is running this program is very low, okay? But you can do a very fast thing. What should you do? This is a very slow machine. After executing this instruction, it's wait for 5 seconds. Let's see. Okay, and what do you do? In the 5 seconds, what do you do? You create a symbolic link. Okay, so you are not changing the behavior of the program. Okay, remember, you cannot change the behavior of this program. This program is still running. It just simply runs very slowly. Okay, so after it checks this, it's going to pause for 5 seconds. Now, at the same time, you're going to run a parallel program. That parallel program is going to actually change. You're going to change this. Now, let it point to the password file. Now, the meaning of this actually file name is different now. At this place, it is just a regular file. Okay, and after that, it becomes a symbolic link and point to the root owner file. Okay, now the meaning is different. You have never changed the behavior of the program, but you have changed the meaning of that file from outside of the program. Okay, so but you got to depend on this program run very slowly, right? But that's not the reality, right? In reality, the program runs very fast. How do we get a chance? How do we get a chance? When the program runs very fast, it's not going to wait for me to type the link command. It's going to run very fast.
To get sleep?
We cannot put this program to sleep because we don't have sleep instruction here.
So can we set a quantum on the CPU?
Set a quantum on CPU.
To get it to switch to the next task and put that process to sleep?
Okay, so to be able to do that, you pretty much need to have a root privilege
Yeah.
if you want to actually change the schedule. Okay, so but you're on the right direction. You're on the right direction. Okay,
Run many programs simultaneously to make the processing slow.
making the program slow, but even though they still won't wait for 5 seconds. Okay, so you can make it slow, but not to that degree. Okay, what do you do? Did you remember how do you defeat the address randomization? What do?
You can try
You try many times, right? Same thing here. There's no guarantee since you cannot control the CPU. So we're going to run the attack program many times. And what you need to wait for is the context switch right in here, right? The program does context switch. Okay, so when I run this program, this program will not just run continuously because you only have this limited number of CPU. At any point of time, the CPU may pause this program and run another process. Okay, and that's what you're waiting for. So you have a window here, although it's a very short window, but you got a chance. Okay, and you have time. Okay, so your goal is to be able to do this during that time window. But you cannot determine when is your chance. You just have to keep trying, keep doing this the linking things, and hopefully when you do this, you are doing this right between 1 and 2. Okay, so that's what you need to do for the lab. Okay, you need to write another process, and you need to run this actually setuid program continuously. Okay, and let it run in a loop, and run your program in a loop. Okay, hopefully, and you win that race condition. Okay, so it will take a while. Okay, but some students get it very fast, still based on the luck. Okay, okay. Here's another vulnerable program, similar. Let me ask you whether you can identify how you can exploit this. So the program is trying to write to that file again. Okay, trying to open this file. Okay, so first it's check whether the file exists or not. Okay, if file exists, it will not do anything. Okay, if file doesn't exist, equal to false, it will create a file. And then after create a file, of course, we're going to write things into that file. So that's what the program is trying to do. First check, and then this is a check. And this is to use. Check and use. Now, what can you do? We don't have access here anymore. But we do have a check and a use. In the previous case, the check is access. The use is to open. So we're trying to use that file. Right? Check on that file, use that file. Here we're checking the file and use that file. So what can you do? One thing I want to tell you, if the file already exists, the open with that option will open the file. We open the existing file. If file does exist, okay, and when you say I want to create a file, I want to use the option create option, okay, but the system says the file already exists. It will just simply open the file, okay, instead of creating that file. If file doesn't exist, it will create and then open. Otherwise, just open that for you. Now, what you want to do, you want to create a scenario where the file doesn't exist at this point. But right after that, you want that to point to the /temp x to point to /etc password at this point. At the beginning, the file shouldn't exist. Otherwise, this is going to be equal to true. And equal to true is going to go to a different branch. So you want to make sure that there's no such file. But right after that, and you're going to do something, link this file name, and to the password file. And then it's going to go to here, right? Because file doesn't exist. Okay, when they do the check here, it doesn't exist. And then it's going to open that file. The file already exists. The OS will just open that. And that you write to that. Okay, the same idea. Okay, and do something between the check and the use. Okay, the question?
So if you have like a second running program
Mhm.
that does that, what does that step break that you drew off to the side there?
You have a what? Can you say again?
Do you have just a separate code running that does the text to etc password?
So idea is you run this program. You run this program in a loop.
Yeah.
Okay, and you run your own attack program in a loop.
Okay.
Your attack program basically just doing this. Link this to that password file.
All right.
And if it doesn't, if your attack is not successful, you break the link, delete the file,
Yeah.
and then later on add a link again. Yeah, I will show you the attacking code. Okay, and right now it's too abstract. But basically, you need to link that and then break this link again, break this link, and hopefully, when you create the link, it's right in between. Okay, that's your only opportunity to win.
So you're really just hoping it will eventually.
Yes, you really hope that it will happen, and it will happen. Okay,
Yeah.
when you do the lab, it will happen. The chance is very low, but since you can run this and overnight, right, 10 hours, 20 hours,
It will.
yes, it will eventually. Yes, yeah, you will find out it will win. Yes.
So what if it was like running for like 2 days straight?
You don't need 2 days, yeah, but maybe when you're very unlucky, maybe you spend 2 days.
Because mine took around 2 days.
Oh, for the buffer flow.
Right.
Oh wow. I'm very impressed. You're very patient.
So I restarted.
Yeah. So yeah. Maybe you're just an unlucky case. Yeah. So maybe next time you'll be more lucky. So yeah. So but as I said, it actually that's how it takes. It's going to be run. Some people get that within 3 minutes, and a few seconds. Yeah. For this one. Yeah. So you'll find out. Yeah. So this is basically the vulnerable program that you're going to use in the lab. So I'm going to skip that. I'm going to show you the attacking script. So you let that vulnerable program run, okay? So and at the same time, and this is the case. I'm going to actually this is the first example, XYZ, and then I need to pass the first one. I need to pass access check. Okay, and after that, I need to link this to the /etc password file. Okay, and so that's what I've been doing. The first one, you can see I'm actually running in a loop, infinite loop. Okay, so and on link, I basically remove that link. On link, just delete that symbolic link. Now, same link to make this link to this file. Okay, you can create any file in your own folder. Okay, make this link to your file. And what is the purpose of that? It to make sure I pass this access, right? Because now symbolic link point to my own file, and access check the real user ID, and of course I can access my own file. So this is really just to pass access system call. Right after that, I'm going to just slip a little bit. Okay, I'm going to slip. This is a microsecond. Okay, so about I think it's a 100th of a second. So I'm going to slip for that. Okay, I'm basically waiting for the context switch. Okay, because right after doing this, if I continue doing this, it's going to be useless. I want to pass the access. I want to let the vulnerable program to get a chance to run. Okay, but I hope that once the vulnerable program finish the access, and it does a context switch, and then I get a chance. That's what I hope. Okay, so when I slip, I'm going to give away the CPU. Okay, now other process, whether it's a vulnerable program or not, I have no control. Okay, but some other process is going to run. Okay, and then after I wake up, I'm going to actually link this. I'm going to unlink this. Now I'm going to let it point to the /etc password file. Okay, and then after that, I'm going to sleep again, and hopefully give control back to the vulnerable program. And hopefully that the vulnerable program is going to actually continue on with the open. And that is going to open that /etc password file. Okay? So that's, you can adjust this, the time of sleep, okay, and that's something that you can do. So if it doesn't work, and maybe increase the value, decrease the value, okay, and adjust it a little bit. Okay, so you do need to give it enough time. Okay, so, and also for this lab, and for some reason we still don't know, and that you may actually corrupt the /etc password file, shadow file. Okay, because we're doing a lot of this race condition things, and you may actually corrupt the file. So it's a better idea to take a snapshot of your VM before you run this lab. Take a snapshot, because once you lose the /etc password, the shadow file, and you cannot log in again. Okay, the VM is still fine, but you cannot log in. Okay, so of course not a big deal. You can just always just download a new VM. Okay, but you lost your code, whatever you put in the code. Yeah, so it's a better idea to take a snapshot. If you don't know how to take a snapshot, okay, and we do have instruction on the website. It's very, very simple in the VirtualBox, and you can take a snapshot. And we recommend you before doing every lab, you should take a snapshot. Okay, so this way you can preserve the current state of your VM. So in case something goes wrong, you can always back to a clean state. Okay, and this is very important. Okay, we still don't know why. Okay, what happened? Why somebody lost the actual /etc shadow file? Okay, in order to create a new account, you need to actually to modify two files. I'm only showing you how to modify the password file. You need to use the same tricks to do this, to modify the shadow file. Okay, so you may have to spend 4 days on that. So if you are very unlucky, yeah. But I hope that's not the case. Yeah. So, but do let me know if you have to spend 4 days. Yeah. And you can also use another file. So all you need to do is find a file which is a privileged file. Okay. So other than the /etc password file, shadow file, and you can use a sudo file, right? Remember, sudo allows you to give a normal user privilege to run super user command. You can create a new account. You do have to create a new account because CD user is already privileged. Okay, it doesn't count. You have to add a new account for another, basically a new account. You call it XYZ, and then give XYZ the privilege, and to run as a root. So you can do this, or you can just modify the /etc sudo, which is also configuration file for sudo. If you can add an entry to that, you can allow anybody to run with a super user privilege. So it's equivalent, okay? And yeah, maybe modify that is better, because even if you actually corrupt this file, you're okay. In the worst case, you cannot run sudo, but you can create a new sudo file. Yeah, it's not a big deal. But these two files too critical, okay? So it's gonna up to you. So is this clear? So you're going to actually work on this in the lab, okay? And I went very fast, okay? Okay, and this is where the quiz is. So the two questions. I'm going to ask you to take out a piece of paper, and for undergrad student, and do write down your name. Okay, I will grade that. Okay. For grad student, you don't need to submit. Okay, so. But you're welcome to work on that. Okay. So this is actually two questions. Okay, I didn't. So question 1, question 2. The question 1 is you can read that. Question 2, and I just added the question 2 before the class, so I didn't actually write down complete thing. So this whole thing should also go to the question 2. Okay. The question 2, the only difference is this code is different. Okay, but this block is the same for question 1 and for question 2. Okay, for the question 2, this is the code. Okay, for question 1, this is the code. Okay, so I want you to write. This is a program which runs with setUID program, which runs with setUID privilege. Okay, I want you to tell me whether that's actually a race condition, whether that's an exploitable race condition. Focus on exploitable means, and you gain the privilege by using the race condition inside of this program. Okay, so and this also came from one of the final exam questions. Okay, and the second question is the same thing here, the same sentence here, but the code is this piece of code. Okay, so does this piece of code have exploitable race condition? And if yes, if no, and explain. Okay, so basically 2 questions. Yes.
Is that the entire code? The question 2 that
It's not the entire code. It's just the snippet of the code, the most essential part. The goal is to really test whether you fully understand the race condition or not. Okay. Okay, that's good. So let's just look at this. Okay, very quickly. So remember, this is the type of attack is we look for the window, right? We look for the window between the check and the use. And that's why this type of attack is also called a time to check and time to use. And sometimes we just call TOCTOU. Time off, not time to. Yeah. Time off, check, time of use. TOCTOU, okay? And that's also another name we use for this kind of vulnerability. Okay? So you're looking for the window, but you need to be very careful whether you can exploit that window or not. In both cases, and they have a window. They both have the window, but in both cases, and none of the window is exploitable. So you don't have any vulnerability inside. Okay? Although you see the pattern, right? There's a time of check, a time of use, the window. For example, here, you have access, you have open, that's a window. Right? Now, in order to exploit that window, what you need to do is you need to actually let this /etc shadow file, right? You need to be able to pass this. First, you need to be past this one. Can you pass this one or not? You cannot. As a normal user, you cannot pass this actually the check. Although the window is there, but you cannot even pass this check. You are a normal user. Your real user ID is a C. You are going to fail here. You're going to directly go to the other branch. Okay? From the paper, it looks like the window is there. But this is different from the /temp/x. /temp/x, that is in a public folder. Anybody can access that folder. And everybody can create a file there. But the /etc shadow file, that /etc folder is protected. You cannot do anything in that folder, okay, unless you're already root. Okay, so that's why a few years ago when I gave this in the final exam, 80% of students did it wrong, because their first impression is there's a window, that's a vulnerability, right? But you really have to look into this whether there's exploitable window. Your first actually the guard is going to actually direct you to the other branch, right?
Access of shadow will return no, and then means not will be a yes, right? For a normal user, the access to he will not have access to shadow file, so it will be a no.
Okay, so it's the same thing here. Okay. So basically, if you can access that, and then it's going to return 0. Okay, if you can access, return 0. Okay, so if not, and you will go to there. Okay, so the second one, of course, looks like there's a check, right? And there's actually the use. But how can you exploit this window? Yeah, you cannot exploit this window. You cannot change the value of this flag. You cannot change that. Okay? So this flag is an internal variable. Okay? This is outside file, which you can change. But if this is an internal variable, whatever you do in the outside, it doesn't matter whether context switch happens or not. You cannot affect the value of this. Okay? So that's actually what I would answer that question.
Is that right? So even with root privilege, you can't access that shadow, then you still can't?
When you run the access is checked in the real user ID. If I'm running set UID program, my real user ID is myself. Even the effect user ID is root, but the real user ID is still myself. Access is going to check whether this real user can access the file. Yeah, that's the main difference. Okay? Script? Yes.
Can I make a symbolic link from my ETC shadow to a file? And that file belongs to C.
So in order to make a symbolic link, you need to be able to modify the file as a normal user. Slash ETC shadow file is a protected file. Right? You can delete that file. And you cannot create a symbolic link like this going to a different place. Is it clear? Okay. Okay, great. Today we're going to actually continue to talk about the race condition. Okay, we talked about how the attack works. Today we're going to look at the countermeasure. So we talked about the race condition attack. Okay, so this is just an example, and we actually went through this. Okay, the problem is the window. Okay, between the check. Okay, so last time, and I forgot to mention the return value of this access is kind of misleading. Okay, so if the user is allowed to modify this file, okay, the return value will be 0. Okay, and so that's why they put this negative before that. Okay, so this is a kind of weird actually the return value, but so that's actually the check. This is a check. Okay, time of check and time of use. Okay, this is to check on this, and then this is time of use. Okay, and clearly there's a window. Okay, and between the check and the use, and the thing that they are checking. So in this case is the /temp/x. The thing that they're checking can be actually, the status of this can be changed during this time window. Okay, so after you check this, and somebody can actually modify the status of this, so basically invalidate your the check. And so this way, after you check, and then in between, if the attacker can do something, okay, and you will end up open a privileged file, a different file. Okay. So now, what I want you to think about is, okay, how can we solve this problem? Okay, how do we actually defeat this race condition? Okay, we have to check. Okay, we have to use. So the window is there. It's difficult to remove that window, but can we do something to actually get rid of one of the conditions? Okay, there are certain conditions, right? Windows, then to be able to modify that object, right? So, and then also you have to take a chance. It's not always that you can be successful, right? And you really have to take a chance. You have to run your code for maybe many hours in order to succeed. Okay, so what could be some idea that we can use to actually either completely get rid of this problem, or make it harder, make attackers' job harder? Okay, so any idea?
Maybe we can make the program not interruptible during executing this piece of code.
Okay, that's going to be very difficult. Very difficult. Okay, so the OS usually do not allow the normal application and to actually take over the CPU, because that's going to cause problems. Okay, user level programs, they don't want, unless it's very, very critical, they don't want you to take over the CPU. Okay, and that can cause a lot of problem in the OS. Okay, while you are running the OS, the kernel has to interrupt. Okay, if you cannot be interrupted, then OS cannot even function. When some packet come into your card, it has to interrupt your program. So CPU can process that actual card, get the data. So it has to actually, all the program need to be interrupted. Okay, so that probably is a theoretical, but it's not going to be practical. Okay. What else?
When the program starts to change the file, can we lock the file to make it available to be read or make any like symbolic link?
Okay. So one of the idea is lock the file. Okay. So if I lock the file, then the other people cannot use the file, right? Cannot do anything to this file, right? So although theoretically this also works, but in practice, OS, the locking mechanism in the OS is a soft lock. Okay, it's not a hard lock, which means it's meant for you to civilize the process. When I lock the file, okay, if you need to access the file, you better check whether there's lock status. If the file is locked, you shouldn't touch anything. So it's meant for civilize the process and to know somebody else is using this, so I shouldn't. But if you say I just want to use it, and you can ignore the lock. Okay, so the lock is not hard actually the lock in the OS. Okay, so it's meant for multiple process to work together on something. But here we are talking about attacker and another process. They don't want to work together. Okay, so that's all. Also, theoretically, we can make it work, but most of OS is a soft lock mechanism. Okay. What else? But those are good idea. Okay.
What if we get notified if the file's changed or been modified?
So in this case, we are not actually modifying the file. We just change the symbolic link. Okay. So now, if you need to monitor this, you probably have to another system to monitor this. Yeah. So the program itself is gonna very difficult to have a monitoring system. Okay. Yeah. So we can put some monitor those things. Yeah. But it's going to be expensive. Okay. So. Okay. Any more ideas? But that's good. Let the idea flow. Okay. Hopefully, eventually, we can get something closer. Okay. Go ahead.
Just don't use the temp directory if you are using security program.
Okay, don't use temp directory. Okay.
Use directory owned by root, or like where only root has access, or that user has access, like home directory or something.
Okay, so avoid /temp. So basically, you're saying, okay, let's save something, save the file X in a different location.
The location which will be accessible by that user whose security program it is. In this case by the root. Yeah.
Right. Okay. That will solve the problem. Let's see. Okay. So instead of using the /temp_x, let's use something in the var directory which is owned by the root. Right. In there we create a /temp, and so that it's only writable by the root. Right. So in this case, we don't even need. So
effectively, you are removing the first condition.
Okay, so in this case, the normal user cannot create anything inside that. That actually take out this condition, right? Okay, that works. That works. Okay, so basically he's trying to destroy this condition. Okay, so even if you're using this, okay, but there's still a window, but between this window, there's nothing you can do. You cannot modify that file, right? That's from symbolic link. So that one is fine. That's very good. Okay, so good. What else? There are actually multiple solutions here. Okay, multiple ideas. So let's see, how do we make this more difficult? So I still want this the using the /temp directory. Okay, I still want to let it run, but let's say the chance of getting into that window And to be able to modify that file during that window is probability is P. If I can increase that decrease that probability and significantly, I can make it harder, right? So how do I, let's see, right now it's P, how can I make it to the P to the 3, right? How can I do that? P is going to be small, right? That's why it's going to take you hours, maybe days to succeed. Now if I actually raise it to the power 2, power 3, power 4, that's going to be making it maybe a month, years. Okay, that'd be great. So how do we decrease the probability? Okay.
Club both those things in one statement.
Can you say it again?
Club both those things in one statement itself. Like if this, do that, like sequentially.
In the one statement,
Yeah.
would that work? So he's saying just to make this one line, right? But it's the same. It doesn't matter. The compiler, make this 4 lines into 1 line is equivalent to that. Yeah. So compiler, they don't care if it's 5 lines or 10 lines or 1 lines. Compiler treat them the same. Okay. So by changing the way how you write that program, it's not going to work. Okay.
Check if the temp_x file is a symbolic link or not. Just to check using if something.
Okay, so he's going to say after this, right? After this, right?
Yeah.
Check again, right? So he has a check here. Now he's using this, but right after he used that, he's going to do another check, double check, right? So now if you actually do the double check, basically do the access again. Okay, let's say just do the access, using the access check again. Now will this work? It's the same? How come it's the same? So before that, okay, let me erase all of this marking. Before that, it's just going to be the /10x file. So you can pass the first check, right? Right after that, you have to link that to the /etc password file, right? You have to change that so you can gain the benefit, right? Right after this, let's remove this. Right after this, I'm going to check using the access again. If you do not pass my access, I will not write to the file. So I add one more check. Before I do a check, after that I do another check. To pass my check, you have to change it back. You will have to change it back. So to succeed in this check, if you do not actually change this access will fail. Okay, because this one says, does real user ID have a permission to modify that file? The answer is no, and therefore I will not write to that file. So you can see there's a check, use, check again. Okay, so definitely now it won't work, right? Or does it? Can still be work? Can attack still make it work? Can they? Now we just add one more check. Okay.
Can I say the possibilities is decreased, but it's still possible maybe.
Very good, very good. So you can see here I need to make this change. Okay. And in order to pass this, I have to make this change again. So I just change it back. Okay. I change it to the /etc shadow file. I have to change it back. Okay. If the probability of doing this is P, okay, now to win this, let's say just probability probably is around P again. So now you decrease that to the P squared. And you make it much harder. Okay. So this actually is an additional check and make it work. Okay. So now if you can check it multiple times, right? You can do access and open again, access, open again, multiple times, and you may make it work. Okay.
But once you open the file, it will be pointing to that old one, right? They are having a pointer to that file by the open command.
Yeah, you will open again. You will open again. Yeah. So let me show you the way. So this was an idea proposed by somebody else. So It's called a check and use, check use repeating approach. And so basically they repeat these three. This is actually access open. Okay, access open. Okay, so it repeats this 3 times. 1, 2, 3, and these 3 pieces of code are identical. Okay, other than these variables are different. Okay, FD1, FD1, FD2, FD3. Now, after that, they're going to compare this FD1 to 3 to make sure they're identical. If they're not identical, and that means you lost the race condition, right? So if you do not touch anything, inside if you don't do anything, and yes, they will be identical. They will open the same file, right? But so to compare this, what we do is just basically compare the inode. Okay, to check whether these 3 files are the same, you check their inode. Okay, and you use this one to get the status, and then compare the inode. If they are the same, write to the file. Okay, now in order to win this, you really have to actually win the race condition here in this window, right? So here you got to win here. Immediately after that, you have to change it back, right? You have to change it back, otherwise you're going to fail this. Okay, so you're going to actually change it back here, that's 2. After that, you're going to change it here, 3. After that, you're going to do it, change it back again, and then 4, 5. So you're going to do a lot of these things, and that makes it much, much harder. Okay, so this is a kind of neat idea, although maybe in practice we don't do this. That's just too much redundant code in there. But that just shows you some of the nice ideas that can be developed. Okay, so this is the one thing. Another interesting idea is to make it atomic, right? We talk about the window is the problem. If we can get rid of the window, right? So there's a check and a use window. And there's a window in between. Now, during this window, and this process can be actually interrupted. Okay, so that's what's called the problem. If you can make this atomic, the atomic means when I do the check and use, I cannot be interrupted. Okay, so this goes back to the idea. Okay, but not the entire process. You cannot make the entire process to be atomic. Okay, because then something is going to go wrong. Okay, but you can make these 2 operations, okay, to be atomic. Okay, so how do we make this atomic? If you can do the both check and use inside the kernel, okay, and you can be atomic. Okay, once you are in the kernel, usually in most of the OS, and you will not be interrupted. Okay, unless there are some high important interruption comes, like network event comes in. But another process will not be able to interrupt you. Okay, once you're in the kernel. Okay, so your process will not be actually swapped out. Okay, so if you can actually do that, and then you remove the window, because now I'm doing the check and use at the same time, right, inside the kernel, not exact the same time, but actually inside the kernel. When I chop in the kernel, I do it in one round. Okay, so this approach, this vulnerable program, okay, when they do the check file existence, probably it's going to chop into the kernel once, and after that comes back, and when you do the open, you chop to the kernel again. Okay, so these two operations, and you have to go get into the kernel twice. Of course, between them, your process can be actually interrupted. The scheduler can schedule another process to run. But if you say, if I can do this both, 1 and 2, just in one run, inside the kernel, okay, and then I get rid of the window. Okay, and so that was actually the idea. So, and it turns out actually you can do that with open system call to do both. Okay, so the open system call, if you just open a file, okay, you still use this. And there's an option. So you have to specify another option. So you have this option, you want to create a file. And you also put another option, says I want to exclusively create. What does that mean? That means if file exists, just don't open it. Okay? Only open this file when the file doesn't exist. So I only want you to create a file. Okay? If the file already exists, just don't do anything. Okay? Don't open the file. So that actually do the checking whether the file exists and open the file altogether in one system call. Okay? So while you're doing this system call, and you cannot be interrupted by another process. Okay? Kernel can interrupt you, okay, but not by another process. So this is called atomic. Okay? And we can also apply this idea to the access. So access and open. The window between access and open. So how do we apply this? So how do we apply this atomic idea? So we can solve this as existent, okay? So how do we modify the open system call? Okay, the solution doesn't exist, okay? I just want to mention. This one exists, already exists, you can use. But what I'm asking you, can you apply the same idea to modify the open system call? So you can get rid of this window. Okay? Can you think about the idea? Okay. Here we have to modify the open system call to add this option. Okay. Once you add this option, checking this option is not difficult. Just look at one bit. This bit is on. Okay. I'm going to make sure that if file already exists, I will just return. Don't do anything. Now I want you to get rid of that window using atomic operation. So let's do it inside open. So let's do the open. Instead of having access, which is a system call, go to the kernel once, and open, go to the kernel and do the second time. Instead of doing that, let's just make it one trip to the kernel. Okay, let's do the so whatever the write. Okay, so just. So let's add something here. What kind of option do you want to add? So now this, as I said, this doesn't exist. So I want you to create that option. Okay, I'm not asking you to think about can I find that option from menu? No, there's no such menu. I'm asking you, if you were redesign this OS, what option would you add to the open system call so we can get rid of this window?
Is owner.
Is owner, okay.
Like if that person who is executing is the owner of that file.
Okay, is owner, okay. So more concrete. So can somebody say more with more? Okay.
Just that one option actually not the same as access.
Okay. Same as access.
Let's call it.
Yeah.
Access. Okay, what does that do? What does that do? If you add this option, what does this option do?
Check the owner of the file. See if I have
check the real user ID. That's great. Okay, so great. I know you guys. That's what you want to say. But so let's say all real UID. We can create this option. So open is only going to use effective user ID. And that's why we have to use access, right, and use open, because access check the real user ID. The open use the effective user ID. We have to do this and creating a window, right? Now if I can modify this open, I will just provide an option. I will tell the open, don't look at the effective user ID. This time, look at the real user ID, right? That solves the whole problem, right? Just ask the open to look at something else, okay? So you can just create that option, okay? And and you can modify the OS. So this is actually the solution that requires the modification of the OS. Okay, and the idea is to use atomic. Okay, this is the key idea. Make it atomic. Okay, get rid of the window. Okay, so lock-in cannot be enforced, and prevent this interruption is going to be hard for the entire process. Okay, but you can actually make this option, this short window, and make it atomic. That can be doable. Okay, so and unfortunately this solution doesn't exist. Okay, and to propose a new options, and you need to get us entire committee to prove this. And so far, and this was not there. Okay, maybe someday they will be there, but this is already there. Okay, so if you want to do this, okay, and you want to open a file, and you want to make sure the file doesn't exist, and you do use this option, that will remove the window. Okay, it's clear? Why does the developer do the access? Why? This is a privileged program, right? So why does the developer actually use access? What is the concern?
Because the program is the same program, so it's running with EA.
Okay.
You check the real user of the file.
Okay, so here the program is running with a super user privilege. Okay, very powerful privilege. Okay. Now, the program needs to do something which does not require the super user privilege, right? It needs to open that /temp_x file. So that's why they want to check. Okay, am I using super user power to open this? Because eventually I'm going to use super user power to open this. So I don't want to open other people's file. I only want to open my own file, right? So that's the whole purpose of this access. So they want to be themselves. They want the process to be themselves, to be the real user ID. And this way, and when they open the file, and you will only open your own file, right? That's the whole point. But the way how this program is written is not the right way to do that. Okay, so think about what are the other ways to do that. I'm a powerful user. I want to do something which does not require my power. That's the goal. It wants to open a file belong to the real user ID. So it needs to do something that doesn't require the power. The approach, you have two approaches. Approach one is to check the things that I'm going to do, the file that I'm going to open, and is this actually my file, right? That's what this program is doing. But this is not the only way. And this is more dangerous. You are still having the power, right? And you just want to make sure I'm not touching other people's file. Okay? What could be the other way?
Can I temporarily downgrade?
Yes, the right way should be just downgrade your privilege, right? Now you don't need the privilege. Why still using the privilege? You should just downgrade your privilege. So instead of still carrying your privilege, checking whether it's safe to actually to do that things or not. That's one way to do that. Okay? But a better way let's just downgrade my privilege. Now this way, even if I make a mistake and the program just crash, it doesn't matter. Okay? If the file doesn't belong to me, I will not have permission. So that is a much safer way. Downgrade your privilege. Okay? Instead of carry your privilege, but checking whether you are allowed to do that or not. Checking is always hard. And you can see here the window, right? And there are many other ways to make a mistake when you check something. But if I just remove my privilege, that's very easy. And then after that, I don't need to check. Okay? If I don't have a power, I don't have a power. Okay? Let's go back to the Superman story, right? So after Superman finished the task, right? Super people, right? After super people or Superman finished the task, right? The Superman's to go back, okay, or to run back, or to fly back. But Superman may make a mistake, right? May bump into somebody. When you bump into somebody, you may kill that person because you're like a train, right? Like an airplane. So that's why when Superman flies, he always have to check whether there's somebody in front of me. If there's in front of it, you have to go right like that, right? So it has to always detect whether there's a danger or whether there's a risk that he's going to pose on the other people. Okay, that checking, okay, and could be very difficult, right? It requires a lot of image processing, right? What if Superman says, I'm already done with my job. Why do I still need my power? Let me turn off my power. I'm just a regular person, right? I have to walk home, no, or take taxi. But there's not much danger, right? If I bump into somebody, we both get knocked down, right? And you're not going to kill that person, right? So you lose your power, but by doing that, you reduce your actually the risk. Even if you make a mistake, okay, you bump into somebody or you get hijacked by somebody, you're still safe. Okay, the term safe means nobody can abuse your power. Okay, so that's exactly what we should do. Okay, so that's actually the idea of the least privilege principle. So when you work on the security and implement security, so one of the principles, this is actually a fundamental principle, and you should always remember is, if I don't need the privilege, I should downgrade my privilege, whether it's temporarily or permanently. Okay, so don't use more than what you need. Yeah, it may be inconvenient, okay, because you have to remember to turn it on, turn it off, or just remove that. So, but that's actually the better practice. So we can just use this to solve the problem. Now, I will just open that. I will just directly open that. But before that, you can see I am setting my EUID to the real UID. I am disable my EUID. Okay. Since I'm using the set EUID, that's a temporary. Okay. Later on, I can actually get it back. Okay. I still remember my effective user ID, so I can actually turn it back on. So that's actually for the much easier solution. Okay, and also much safer. So you don't need to worry about I need to modify the OS. You already have an OS support, and disable your privilege. Okay. And then after that, when you open this file, yeah, they can still actually change it to the etc shadow file or password file, but this will fail. Okay, you won't be able to open this file with write permission. Okay, so that's the idea of how. Okay, so now I just want to make sure you understand this idea, because that's going to be the next one is going to be a pop quiz. Okay, so make sure you understand this, and if not, then ask question. Okay. Okay, so I'm going to give you 10 minutes. Write that down, submit that. Okay. So basically, I'm using the least privilege principle, okay, that we just saw, how we solve the race condition. Now I'm going to apply the same idea to solve the buffer overflow. Okay, that's a buffer overflow, and before the buffer. So let's see. Let me give you more the string copy, which has a buffer overflow. Okay, so I'm going to disable my privilege. So there's a function foo and return. Okay, I'm in the main function. So I'm going to call foo. Since I know inside the foo, and there's actually a string copy, and they may have a buffer overflow. Okay, so I'm going to add something here, disable privilege. Because inside the foo, I only do the copy. Why do I need the super user privilege to copy the memory? Right? There's no any privileged operation inside. So I should disable my privilege. Okay? Basically set EUID to the real UID. Okay, RUID. Okay? Get the real user ID. Set EUID to real user ID. Therefore, your EUID right now becomes seed. Right now, we are running with the seed privilege. That's real user ID instead of 0. Okay. After that, I'm going to enable that again. Okay. You can set EUID to that actually to the effect user ID again, and you get it back. Okay. So inside of foo, you know you don't have any privilege. You don't have any privilege operation. Okay. So question, right? Not answer. Okay. Yes.
Is this system using any of the countermeasures that we discussed?
No countermeasure, okay, no countermeasure. So we remove all of the countermeasure, return to the executable stack and randomization. Let's remove all of them, okay? So this is a system that doesn't have any countermeasure, and you are trying to protect your own program. This is a setUID program, running with a root privilege. So that's how you disable your privilege, right? Just like what we did in the race condition, okay? Let's look at this, yeah. So now I talked to several of the group, and most of you guys get the first part right, okay? So inside of this, you can still jump to, let's say, the share code. Yeah, thank you. So you can still do this the share code, okay, and the return, and it's going to jump to here. Okay. Now when you return, okay, you are returning here right after privilege gets disabled. So when you return to here, the share code will be executed. But do you get the pound sign or just a normal dollar sign? Normal dollar sign. Because the effective user ID, when you run this one, the EU ID is going to be the seed. And then the share, of course, is going to actually just display the normal, the prompt, instead of the pound sign. So you don't get the root privilege. Okay, so a lot of students just conclude this is safe. And because you only get a normal user, right? And you don't gain anything. But think about, what if I can modify the share code? Why should I use the same share code? Right? I'm not restricted to use the same share code. So what if you can allow to modify the share code? What would you add to this share code? So you don't get the normal share prompt. You really get a pound sign. Exactly. So the first thing you do when you enter the share code, you just set the EU ID and choose 0, right? So the first thing, of course, you have to turn this into the instruction, okay, the binary code, okay, the inter 80 kind of thing, right? Remember, the inter 80 is actually the interruption, okay. And so you need to find out the number, the index for this system call. Right? That's all you need to do. You add this actual instruction at the beginning. You turn it back on, right? You turn it off, but the first thing I do, I turn it back on. As long as I am allowed to turn it back on, I can turn it back on, right? You can turn it back on here, right? Why can't I do it in here? So this solution looks like it can actually defeat the buffer flow attack, but the attacker will be able to bypass that. Okay, so I want you to think about why would this the least privilege principle can be applied to the race condition, but cannot be applied to the buffer flow. Why? What is fundamental difference between these two? Okay.
Because in the race condition we cannot modify the code, but here we can.
Very good, very good. So in the race condition, you can see we never change the program, right? The flow of the program has never been changed, right? We just actually play the tricks of that, actually the /temp x file. But we did not change any code. We did not inject code to the race condition, the program. But in the buffer flow, you can inject code. So the difference is code injection. So if you actually do not have a code injection, okay, and the least privilege principle may work, okay, but also depend on some other special scenario. But most likely they can work. But when you can inject code, okay, now if you only temporarily disable that, and there's no way actually you can prevent actually the injected code to turn it back on, okay, if it's reversible, okay. So that's actually the main difference. What if I permanently disable that? Instead of disable that, I just permanently remove the privilege. So for example, after I finish my task, I'm just going to permanently remove. Okay? So you can, instead of using the set EUID, you can do the set UID to the RUID. set UID basically is going to actually permanently now and remove that actually the effect user ID. Okay, and also the real user ID make it basically you lose privilege after doing that. You cannot get it back. Okay, so if you permanently doing that, then that's okay. Okay, so if you're already done with your task, you say I just want to call foo, maybe do some cleanup. Okay, in that case you're safe. Okay, because if the program trying to do the set UID 0, you cannot. This will fail. Okay, set UID 0 means remember there's 3 user ID, right? There's an effect user ID, and there's a real user ID, there's a saved UID. And this saved user ID basically decides whether you can get it back or not. Okay, so when you set a EUID, the saved user ID is still 0. You still have 0 in your pocket. Okay, and therefore you can turn it back on and off. Okay, you're okay. But once you use a set UID, say I'm going to set all these 3 UID to seed, and now this will become seed, and that's it. You will never get it back because now system doesn't even realize you had that privilege before. Okay, so that's why if you say I want to set a UID to 0, the system is going to look at do you have a 0 in your pocket, and no, and the system is not going to give you the privilege. Okay. So in that case, that works, but it's restricted to the situation when you don't need a privilege anymore. Okay. So when you write this privilege code, that's what you need to think about. Okay. And so if I don't need the privilege, I should just remove that. Okay. If I still need that, I can temporarily disable that. But you need to understand that has a limitation. Okay. It's only going to solve certain kind of problem, but not code injection problem. When the code can be injected, they can overwrite your decision. Okay? There's another solution in the Ubuntu Linux system. It's called a sticky link protection. Okay? So that is more specifically designed for the /temp. Okay? So for the /temp, a lot of the race conditions happen in the /temp directory. So they actually come up with this protection. Okay? So if you set this protection to 1, okay, what this means is, if you look at the documentation, it's kind of very misleading. So what it means is we did some of the investigation, and so if you want to open a file, okay, if you want to open a file and open a file in the /temp directory while this protection is on, okay, and what's going to happen is those are the conditions. Okay, if the effect user ID is this, okay, and the owner of the directory is this, and the symbolic link owner, there are 2 owners. That's why the documentation, and if you read that, it's going to be very misleading because it involves 3 UID here. Okay, so we said, okay, just make a table. And so now only in this condition, and this condition, will this be denied. And for the others, you can still actually trace that symbolic link. So this is to prevent you actually follow a symbolic link under certain condition. Okay. Now, tell me in our attack case, which role actually prevent that from happening? Protect against the race condition. Second one means the follower is a seed, but the EUID actually is the root, right? You mean second one of this, right? Second deny, okay. So yeah, in our case, the effect user ID is root. Okay, the directory folder, which is /temp folder, is owned by root. Okay, but the symbolic link owner is a seed. It's a normal user. Okay, in this case, OS will not allow you to actually to follow that link. Okay, even though you can change that, but once you try to open that, the open will fail. Fopen will fail, because system says this is dangerous. You are following a link created by the user in a privileged mode. Okay, and the directory is owned by /temp. Okay, if the folder is owned by you, okay, so in this case seed root seed. If you look at this condition, if actually the folder is created by you, and you create a symbolic link inside of that, you're still okay. You can follow the symbolic link inside your own directory. Okay, so that's just one of the countermeasures. I don't want you to remember this. I had trouble remember this. That's why we decided I asked my student, so why don't you just write a program? Okay, try all these conditions and let me know the table. If you read the description, I tried very hard trying to read the instruction, the manual. I couldn't understand what they mean because it involves 3 user ID. So eventually I said, just write a program and tell me the result, give me this table. So I just want to show you, and this is just one of the countermeasure. Yeah, I don't particularly like this countermeasure. Yeah, first it's very difficult to understand if you can't understand how they use it, right? So, but it just shows that you can do something in OS level, and trying to prevent some condition, and this is what they're trying to do. The reason why they want to allow this because they thought that those are legitimate. They think only these 2 are dangerous, okay, and then that's why I deny this too.
Why is the second one dangerous? Like, what is the risk in that?
I don't know. Sorry. That's why so you may come up with some interruption for that, but I'm not going to try that. Okay, I'm not going to try that. So this one makes sense. Okay. The other one, basically, whoever designed this, they think these are the dangerous situation, right? So they decide not to do that. Okay. But as I said, I'm not really don't want to remember all of this, and you're going to waste a lot of brain power to remember those things. Yeah. But to know that for this kind of problem, you can solve this problem at a different level, right? This is you solve at the OS level. The atomic solution is also solved at actually the system level, OS level, right? We also look at how can I write a program in a safe way, right? We talk about 2 solutions. Right? We try this multiple times, right? We try the redundant code, and that makes the attack more difficult, right? And another way is we use the privilege principle. That's what I want you to learn. Okay. The most important thing to get out of this is if this principle applies, and this usually